The kidney has been a concern since the 1960s, when we had an anesthetic called methoxyflurane. As I indicated a moment ago, methoxyflurane was metabolized to an extent that isn't equaled by any of these other anesthetics. 3/4 of the anesthetic was metabolized, producing a very high concentration of serum fluoride. And this high serum fluoride concentration was thought to be the genesis of renal failure that it was associated with methoxyflurane. How was this renal failure manifested? Does anyone know? Anyone know how it was, James?
It's a high output renal failure.
A high output.
Vasopressin resistant.
And vasopressin resistant. So if you give vasopressin, what should that do?
In the face of methoxyflurane? Or
No, just normally, in you and me.
It will slow down production of urine.
And it will concentrate the
and
urine.
Concentrate the urine.
And when we had someone who had this injury from methoxyflurane, they could not concentrate the urine despite the injection of vasopressin. And they could actually have renal failure. So this was a significant problem. It was one of the major reasons why methoxyflurane is no longer used in humans. The other reason is that it is so soluble relative to the other anesthetics that recovery could be delayed, even with the enormous metabolism of methoxyflurane. So we're concerned. We're concerned that this high fluoride concentration might produce renal injury. We have a concern about renal injury then in association with fluoride production. We know that all of the modern anesthetics are biodegraded to produce fluoride, but some of them aren't biodegraded enough. What would those be? What would those be? Desflurane. And the other one is? Isoflurane. What about sevoflurane? Is there enough fluoride production with sevoflurane?
There's enough, but it's mostly by hepatic breakdown and not so.
Mostly by hepatic breakdown. And you're getting to something that we're going to be talking about in a minute. With methoxyflurane, it was thought that a level of 50 micromolar serum fluoride would be the threshold for production of renal injury. When you got above that, you had evidence, as James has suggested, of a vasopressin-resistant injury to the kidney. And the higher you went on the serum fluoride levels, the worse the injury got, until you got to levels where you had renal failure. We know that these levels can be reached with sevoflurane. We have produced such levels in human volunteers, where we've given sevoflurane for 8 hours of anesthesia. In fact, we got levels in excess of 100 micromolar. So you'd think sevoflurane should also produce renal injury, particularly if you've given it for a long time at a fairly high concentration. But there is limited or no evidence for renal injury under those circumstances. We tested these volunteers. We challenged them, and they could concentrate urine quite well, thank you. So there wasn't a problem with these volunteers. Sevoflurane has been shown to produce no changes in serum creatinine under a variety of circumstances. Under circumstances where there was pre-existing renal injury, where you'd think, well, the kidney is more vulnerable to the noxious effects. It's been tested in patients with heart disease and prolonged anesthesia and repeated anesthesia. And in all these cases, there's no real evidence that renal injury occurs. So why does sevoflurane differ from methoxyflurane in this regard? Tell us the answer.
Because the fluorine is a metabolism by the hepatic cells and not by the renal tubular cells. So
and in the case of methoxyflurane?
It was the renal.
It was also metabolized by the renal cells. And that's what this slide says. So if you've got production of fluoride in the kidney, it means that the serum fluoride levels don't really reflect the ambient fluoride levels in the kidney itself. If the kidney is producing fluoride, the levels will be higher. And it's those higher levels that are thought to be the genesis of the damage with methoxyflurane and the absence of the damage with sevoflurane. There's another possibility, though, for renal injury from sevoflurane, and we discussed that in the chapter on physical properties of the potent inhaled anesthetics. And I'd like to review that again for you again and add a little more information. We know that sevoflurane can be degraded by absorbance to what? Compound A. That's a vinyl ether, a highly reactive compound that can combine with any protein that it meets. We know that compound A can produce renal injury in rats. That's generally agreed. These are data from several reports showing the percent of corticomedullary necrosis, that is the corticomedullary junction necrosis in rats, as a function of compound A dose. Now that's dose. It's not concentration, it's dose. That is a number of parts per million, a concentration, given for a certain period of time. So if you had 100 parts per million given for 1 hour, that would be 100 parts per million hours. If you had it given for 2 hours, that would be 200 parts per million hours. And you see that when you get above about 200 parts per million hours, you start to see necrosis of kidneys in rats. And as you go higher, you get more necrosis, and you reach a point here between 1,000 and 1,500 parts per million hours where you get complete necrosis, the corticomedullary junction, and you get death of the rats. Well, that's impressive. What's also impressive is that if you check the serum creatinine in these rats, you don't get any evidence of injury from creatinine until you get well up on this curve. No increase in creatinine. Creatinine stays normal. Creatinine is a function of what?
Muscle breakdown.
It's a function of muscle breakdown. That's correct. But the serum creatinine level is
glomerular filtration.
Is a function of glomerular filtration. So if glomerular filtration remains normal, tubular damage, but glomerular filtration remains normal, you may not have any change in serum creatinine. And that's what you see with this form of injury. Now, there's no argument that this injury occurs in rats. All the investigators who've looked at this have found the injury. But there is an argument about whether these results apply to humans. And the argument centers around something called the beta lyase pathway. The argument is that renal injury from compound A results from compound A degradation via the beta lyase pathway. Now, if there's a difference between rats and humans in the beta lyase pathway, perhaps there should be a difference in the toxicity of compound A. Humans have much less beta lyase than rats, so they should metabolize compound A less via this pathway and be less vulnerable. Now, what is the beta lyase pathway? Here it is. Here it is, the beta lyase pathway. You have compound A combined with glutathione. What's glutathione? Anybody know what a glutathione is? It's a tripeptide. What does tripeptide mean? Tripeptide. 3 amino acids, one of which is cysteine. So glutathione, which exists all over the body to protect against this sort of thing happening, to protect against highly reactive compounds, to combine with them and neutralize them, combines with compound A to produce glutathione S conjugates. The S stands for sulfur, and it's the sulfur on the cysteine that combines with compound A. Then we have these enzymes which split off one by one the amino acids. So you split off the first, you split off the second, you're left with cysteine combined with compound A. And that is divided by beta lyase, split off so that the sulfur remains on the compound A, and that sulfur-containing compound is this reactive thioacyl halide. And that's what injures the kidney, so the proponents of the beta lyase theory would have us believe. Now, there's a problem with this theory. The problem is that if it's true, then if we give various inhibitors of the pathway, we should minimize the toxicity. But you don't. In fact, with one of these, you actually increase the toxicity. Don't decrease it, you increase it. If you deplete the stores of glutathione in the body, what should that do to the injury from compound A? It should decrease it, but it increases it. So the story is not clear. It's a bit muddy, a bit muddy. And indeed, there is evidence that humans can be injured from compound A. And the evidence comes from 3 or 4 studies of prolonged administration of sevoflurane to humans, either patients or human volunteers. Studies in which the threshold that we noted earlier for rats is exceeded, something above 200 parts per million hours for the receipt of compound A. In this study, volunteers were given either sevoflurane or desflurane, sevoflurane on one occasion and desflurane on another, in fact, for 8 hours or for 4 hours or for 2 hours. This is the 2-hour study, this is the 4-hour study, and this is the 8-hour study. They were given the sevoflurane at 3% at a 2 liter per minute flow rate, or desflurane at 9% at a 2 liter per minute flow rate. After the anesthesia was done, the volunteers were tested for the amount of urinary albumin. What does urinary albumin, if it exists at an abnormal level, indicate?
Renal tubular damage.
No, it's not renal tubular. You had one of 2 chances. It was either going to be the tubules or the glomerulus. It indicates a leaky glomerulus. I should really stand corrected because tubular damage can increase the amount of albumin in the urine. But the primary cause is glomerular injury. So with sevoflurane given for 10 MAC hours, that is 8 hours of sevoflurane anesthesia, you can see that there is an abnormality as indicated by the amount of albumin in the urine. And at 4 hours, in fact, this is statistically significantly increased relative to desflurane, but the degree of injury is minimal. You can also look at the amount of tubular enzymes that come out in the urine. Tubular enzymes shouldn't come out in the urine if the kidney is not injured. This is the average urinary alpha-glutathione transferase from the kidney cells, from the tubule cells, that appeared in the urine after the 2-hour anesthesia, the 4-hour anesthesia, or the 8-hour anesthesia. With sevoflurane, there was a dose-related increase. With desflurane, there was no increase. That is, with an 8-hour anesthetic, with something like desflurane, there is no injury to the kidney. With an 8-hour anesthetic with sevoflurane, there was evidence of injury. Now, the people who argue that even this doesn't indicate that injury can occur argue that these measures are artificial ones. They're too sensitive, as it were. I would like you to look at this table, though. We know that renal injury in rats can be defined by all of these factors: renal necrosis, proteinuria, glucosuria, enzymuria, and at very high levels of injury, increased creatinine, but at levels that produce these changes, there's no necessary increase in serum creatinine. Necrosis hasn't been determined in humans. Does that mean it doesn't occur? Well, we don't know. It's not been measured. No one's willing to biopsy the human kidney after sevoflurane anesthesia. But all these other factors, which appear with necrosis in rats, do appear in humans when the threshold dose of compound A is exceeded. Now, how do we minimize this threshold dose? What are the determinants of the production of compound A? What are they? We've gone through them. Let's recall what they are. Give me one.
Length.
Length of anesthesia. What else?
Temperature of the absorbent.
Temperature of the absorbent, a crucial factor. What else?
Concentration of the sevoflurane.
The concentration of the sevoflurane. Sure. What else?
Flow rates.
Flow rates, which again relate to the temperature of the absorbent, don't they? But flow rates, because if you've got a higher flow rate, how does that protect you?
It helps wash out the compound A.
It helps wash out the compound A. So there are a number of ways we could minimize the production of compound A and eliminate even this very modest threat of renal injury. And we've listed those here, and you've given us the answers to the question. The only thing we hadn't mentioned is the monovalent bases, which are important to the production of compound A. There was an OR scene in which we discussed this issue, and let's run that now. We're giving 6 liters of flow, fresh gas flow, into the system, 2 liters of oxygen and 4 liters of nitrous oxide, along with our sevoflurane. Is there any danger under these circumstances that there could be renal injury from compound A?
No, I would think with such high gas flows that none of the gas is actually being rebreathed, that we shouldn't have any problems with compound A production.
Okay, let's lower those flow rates to 1 and 2 liters per minute. Now it's a total of 3 liters per minute. Do we have any rebreathing now?
You have partial rebreathing.
Partial rebreathing. Is there any risk from compound A under these circumstances?
No, I would think that the levels of compound A that are actually being produced are still fairly low, that you won't see actually any renal injury.
Okay, and why are the levels low?
Because you have your high gas flows.
And what does that do to the carbon dioxide that gets to the absorbent?
Basically, it's decreasing the amount of carbon dioxide that actually gets to the absorbent, which helps. And a decreased amount of carbon dioxide decreases the temperature of the absorbent, which also decreases compound A production.
So the temperature just doesn't get very high in the absorbent at this flow rate. Right. All right, now let's go down to a lower flow rate. Let's go down to 500 cc's of nitrous oxide and 500 cc's of oxygen. Now, do we have partial rebreathing now?
Yes.
Again, we have partial rebreathing. Now, is there any risk from compound A?
I would think it'd be minimal if your procedure was under 2 MAC hours for sevoflurane.
Is that what the package label says?
Yes.
We're allowed to do this. Is that right?
Yes.
But what happens if we go beyond 2 MAC hours?
You need to increase the flow to 2 liters per minute
This is a higher risk. Why?
because you have a higher production of compound A.
Okay, and more rebreathing of that compound A. Why don't you lower the flow rate to 300 and 300? So now our total flow is 600 cc's per minute. Is this permittable?
No. The minimum flow is 1 liter per minute.
So
with
we shouldn't go
sevoflurane.
below that
Right.
1 liter per minute flow rate.
Right.
We have an enormous history with sevoflurane now, a history which indicates the safety of this wonderful anesthetic. And there may be 1 or 2 reports of mild injury, but the history is that with tens of millions of anesthetics, they're really a trivial or negligible or perhaps even no reports of renal injury. Why is it that when we've got evidence that if you test it in volunteers and you look very carefully in patients, you can find some evidence of injury, why is it that we haven't seen more reports of renal injury after sevoflurane anesthesia? Michael?
I believe that with humans, even though you see those changes in the proteinuria, et cetera, those are transient usually and return back to baseline.
Right. So in part, no one reports it because it just doesn't last. It's not a problem. What other reasons are there?
Primarily because most anesthesiologists or anesthetists are using a higher flow rate, so the incident is less.
So if you use a higher flow rate, you've eliminated the problem. That's right. And there are actually many reasons why we just aren't seeing the cases. The threshold is pretty high. You really have to go for a long period of time before you're going to see injury. The cases that we do are just too short. We don't use high sevoflurane concentrations. Most of us wouldn't use 3% sevoflurane for 8 hours. The absorbent may be partially used. Now that's something that most people don't talk about very much. But if you use an absorbent, the first bases that get used up would be which ones?
Monovalent.
The monovalent bases. So if you've used the absorbent, well, the potential for production of compound A is reduced. And rarely do we look at the measures that would indicate renal injury. We look at creatinine, perhaps. That's a routine measurement. But we don't look at urinary albumin excretion. And certainly we don't look at the enzymes that might arise in the urine. And as Michael suggested, the injury, if it does occur, is transient, and you're apt to miss it. If compound A is going to be a problem, it's going to be a problem in what cases?
For cases that last 5 hours or longer.
Like this one, or this one?
This one and this one.
And
There-
that's in a group of how many cases?
There are about 57 cases posted today, so less than 10% of cases would be a problem.
So you're already down to no more than 10% of the cases that you might do. And in those cases, if you don't use a high sevoflurane concentration, or you use a high flow, or you just don't even look at potential for injury, you're not going to see it. So we don't see it. Nonetheless, the concern exists, and it alters, at least in North America, in this country, the package label. And the package label simply warns this. It says, as Jennifer said, you don't use an inflow rate less than 1 liter per minute. And you use a higher flow rate if you're going to go for more than 2 Mach hours. So you use 1 liter per minute if you're going to go for 2 Mach hours or less, but if you're going to go for more than that, you better use a higher flow rate to minimize the potential for injury from compound A.